Hi everyone. You have now survived 2 units with me in chemistry, so this is going to be the start of the next one. We're going to be talking about ions and ionic bonds. So the first thing to talk about before we talk about ions is ionization energy. So what is that? It is the energy that is required to remove an electron from an atom. So I mentioned a bunch of times when we were covering atoms and I asked you how many electrons an atom had, I was very specific to say how many do they have in neutral state, because atoms can lose or gain electrons depending on the situation that they're in. So when an atom loses or gains an electron, it becomes an ion. Now, to lose or gain that electron requires an amount of energy, and that is what ionization energy is. The trend of ionization energy is this. So you see that from the bottom of the periodic table to the top of the periodic table, ionization energy increases. Now, what that means is when you are talking about hydrogen, it would take more energy for hydrogen to turn into an ion than it would for lithium to turn into an ion. It also increases from left to right. So it's going to take more energy for fluorine to have an electron pulled away from it than it would take for oxygen to have an electron pulled away from it. So what I want to note here specifically is that I'm not talking about the amount of energy to gain an electron. I'm talking about the amount of energy to lose an electron very specifically. So that's going to become important as we go along. So let's talk about what a chemical bond is, because atoms become ions and they bond with each other. So a chemical bond is a force that's going to hold 2 atoms together. Valence electrons are going to be what controls how atoms are going to bond with one another, okay? So a chemical bond is an attraction between the positive nucleus of one atom and the negative electrons of another atom. So we learned back when I was talking about atoms in general that protons are positive and electrons are negatively charged. So protons are found in the nucleus, so that's going to be your positive nucleus, and electrons are negative, so hence your negative electrons. So think about magnets. There's a positive and a negative end on each magnet. If you've ever tried to put 2 positive ends of a magnet together, it doesn't work. They repel each other, just like protons would repel one another. Electrons, negative, negative, would be the same thing. They tend to repel one another, but protons of one atom and electrons of another atom are going to be attracted to each other. And when that happens, we have a chemical bond. Okay, so elements are going to want to be like noble gases. Sometimes we refer to this as noble gas envy. Why do they want to be like noble gases? Well, that explanation is pretty simple. Elements want to have a full valence shell or a full outer shell of electrons. And noble gases having 8 valence electrons, that is a full outer shell. So the rest of these atoms, when they ionize, they want to have a full outer shell. And to do that, like let's say lithium only has 1 valence electron. So the easiest way for lithium to gain a full outer shell is not to gain 7 more to achieve that 8, but it's actually to lose that extra electron, and then the shell underneath that would have a full outer shell. The same with magnesium here. It's easier to lose 2 than it is to gain 6. So that is going to be why atoms ionize as they do. So there's a couple different types of ions that you can have. You could have a cation, which has a positive charge because that atom is going to lose 1 or more valence electrons. Now remember, electrons are negative. So if you are losing a negative, you are going to be positive when you are ionized. So an easy way to remember that I like to use is cations have a positive charge, like cat paw. So that's how I remember that. Usually cations are going to be metals. The only exception to that is going to be hydrogen. Hydrogen is a nonmetal, but we place it over in this section because it is a positive ion, okay? So remember, cations are generally metals except hydrogen. So here's an example of a cation. Sodium is going to have a positive 1 charge. We call the sodium ion the sodium ion. We already looked at its electron configuration. So let's just kind of break that down and analyze it real quick. Sodium, if you were to write out its electron configuration, has a 1s2, 2s2, 2p6, 3s1. If sodium were to lose that 1 extra electron in its 3s energy level, then it's going to look like neon. It's going to have the 1s2, 2s2, 2p6, and have 8 electrons in its outer shell because of these 2 guys right there. Okay, so like I said before, it's easier for sodium to lose 1 than to gain 7 more. Okay, so next, let's talk about metal ions. You're going to find metal ions that are predictable in their charges in groups 1, groups 2, and groups 13. So group 1 is going to have a +1 charge as an ion. And if you look at your periodic table, you'll notice this pattern. Group 1, as I had everybody write down, has 1 valence electron. When it loses that electron, you are losing 1 negatively charged thing, so you gain a charge of +1. So to give you an idea of why that is, let's just, for a second, let's look at lithium. Lithium is going to have 3 protons in its nucleus. Okay, I'm leaving out the neutrons because they are neutral and they don't matter in this instance. It also has, in neutral state, 3 electrons. So we have 3 negatives out here. So we have 3 negatives and 3 positives. So in neutral state, those cancel out. The overall charge is 0. But what happens when lithium, which is in group 1, by the way, ionizes, it loses 1 of these electrons. So 1 of these electrons goes away somewhere, somehow, somewhere. The new form of lithium is still going to have 3 protons in its nucleus, but now it only has 2 electrons floating around it. So what's happening here is we have 3 positives in the center, but we have 2 negatives on the outside. 3 minus 2 is a +1. That is where that charge is coming from. Okay. Group 2 is going to have a charge of +2 when it ionizes. So once again, I'm going to draw that out for you. Let's try magnesium at this point. Actually, you know what? No, I'm going to do beryllium instead. So beryllium is going to have 4 protons in the middle. In neutral state, beryllium has 4 electrons floating around the outside of it. When beryllium ionizes, though, 2 of those electrons go away somewhere. And so its new form still has those 4 protons in the center, but now only has 2 negative electrons. So we have 4 plus our -2 is going to give us a +2 charge. That's where that's coming from. Okay? And group 13, we're going to skip all the way over to group 13 because all those groups 3 through 12 are transition groups, so they can have different numbers of valence electrons depending on their situation. So we skip to group 13, and group 13 is going to have a positive 3 charge when those elements ionize. Okay, so that's how that's working for metal ions. Like I said, transition elements do exist. They are also metal ions. They also have a positive charge, but the difference there is that they have a partially filled D shell. So we talked about D shells. When they lose electrons, they get this pseudo noble gas configuration that's happening, and their charges are going to vary. Sometimes it could be +2, +3, +4, +1. It depends on the element, and it depends on what that element happens to be bonding with. So we are going to tell you somehow, some way, what charge any transition element has if I ask you to do something with it. So here's an example of a transition element. Copper is found in the D block. Copper could have copper could be a +1 ion, it could be a +2 ion, it could be a +3 ion, or it could be a +4 ion. Again, it depends situationally what's going on with copper and what it's bonding to at that given time. Not all the transition elements have this many variations, but some of them do. So be aware, if you're looking at a transition element, you cannot reliably say what charge it has unless you have more information. Okay, so then the other option for a type of ion is a negative ion formation. A negative ion occurs when an atom is going to gain one or more valence electrons when it ionizes. So instead of metals losing them, now these nonmetals over here are going to gain electrons when they ionize, gaining a negative and attaining a more negative charge. Usually, again, nonmetals are going to be anions or negative ions, but not always. Again, hydrogen is a nonmetal but is a positive ion, so hydrogen is going to be your exception to that rule as well. We call negative ions anions. We spell that out like this, anion. So that's where this picture is coming from. That kind of looks like onion, and onions, generally people think they smell bad, so that's a negative connotation. If you remember it like this, that's great. I just remember it as the opposite of cations that have the positive charge, so whichever method works for you. Like I said though, negative ions are usually nonmetals. They are, again, trying to obtain that noble gas configuration with the full outer shell of electrons. We name them a little bit differently though. So instead of, like with metals, we just name sodium the sodium ion, you actually name nonmetal ions by adding IDE to the end of its name. So let's say chlorine, for example. If that was going to ionize, it would turn into chloride. See how we've replaced our INE with an IDE. That's the difference there. Okay, so you have to keep that in mind when we're naming those things, because I will ask you to name ions and I will ask you to name compounds. Here's an example going off of chlorine once again, but expanding that explanation a little bit. Chlorine is in group 17 and it's going to have a -1 charge. That is a chloride ion, okay? Instead of saying chlorine ion, we call it a chloride ion. Its electron configuration in neutral state is 1s2, 2s2, 2p6, 3s2, 3p5. So let me go ahead and point something out to you really quickly. So electron configuration for chlorine in neutral state, once again, 1s2, 2s2, 2p6, 3s2, 3p5, right? So if you were to look at that last row on the periodic table, so that's these two, you would notice that the amount of electrons adds up to 7. But I already told you that in a noble gas configuration, 8 is the aim, because 8 is a full outer shell. So it's easier for chlorine to just gain one other electron than it would be to lose 7, to go backwards. So that's why chlorine, if it gains one electron in that last part, you would then have 8 in the outer shell, which mimics the electron configuration of argon. Again, that noble gas envy is causing those atoms to act the way they do when they ionize. So let's just take a little bit of a closer look at what those are looking like specifically. So we have group 15. So I'm going to talk about nitrogen for group 15. Nitrogen is going to have 7 protons. It's element number 7, so it has 7 protons. So let me just sketch that out real quick. 1, 2, 3, 4, 5, 6, 7. Again, I'm ignoring the neutrons because they don't have a charge. So we have 7 positives in the center, okay? In neutral state, nitrogen is also going to have how many electrons in its outer shell? Well, that is going to be a little bit different than the metals that I was talking about, because in its outer shell, it's only going to have 5 electrons. So nitrogen has something going on with it. So I'm going to do a thing here. So let's call that its inner shell real quick. In its inner shell, it's going to have 2 electrons floating around. And if we were looking at the electron configuration, those 2 electrons would be represented by our 1s2 in that inner shell. But nitrogen is also going to have an outer shell, or a valence shell. And in that case, it's going to have 5 floating around in its outer shell. So if we draw that out, we're looking at this and we go, okay, well, we have 7 electrons and 7 protons. So 7 minus 7 is 0. But if we change the number of outer electrons, then that's going to change what the charge is. So nitrogen, it's going to be a little bit easier for nitrogen to gain electrons than it is going to be for nitrogen to lose electrons. So what nitrogen is going to do is it's going to gain 3 electrons. And so those electrons, I'm going to do that in a different color once again. Those electrons are going to come in and populate that valence shell. But now if we do our raw amount of positives and raw amount of negatives, we still have 7 positives, but now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 negatives, which gives us a -3 charge. So that's where that is coming from, okay? So if I were to now talk about group 16 instead, let's just talk about that for a second. I'm going to just not erase my entire drawing because it's going to be easier for me to just add on to it. Let's say we're talking about oxygen now. Oxygen has 8 protons, so that's 8 positives in the center. It's still going to have those inner shell 2 electrons, but it also has that outer shell. And so that outer shell for oxygen in neutral state is going to contain 6 because it's in group 16. So we have 1, 2, 3, 4, 5, 6. So let's look at the math for a second. We have 8 positives, and now for this in neutral state, we have 8 negatives. That's going to give us a charge of 0. Oxygen is going to gain 2 rando electrons from somewhere to get 8 electrons in its outer shell, which is what it wants. So those 2 are going to pop in from somewhere else. Now we have 8 protons minus a total of 8 electrons plus our 2 inner electrons, a total of 10 electrons, giving us a -2 charge, which is what is happening with oxygen. The same for fluorine. I'm not going to draw that one out because fluorine is going to have 9 protons. It's going to have 2 inner shell electrons and 7 outer shell electrons. So to gain 8 in its outer shell, it would only need to gain 1 additional electron, giving that overall charge of -1. So let's talk about group 14 for a second, because group 14 is important. You might be thinking to yourself, well, group 14 is special because it doesn't really matter. If it has 4 valence electrons, it could either gain 4 or it could lose 4. And that doesn't matter. Like, mathematically, it's not obvious which one it would do. Whoops, I went too far. It has 4 valence electrons because it's in group 14, and you've all drawn the electron dot structures with me, so you know that. So for group 14, it's going to depend what's going on. So you'll notice that the staircase kind of cuts group 14 in half, right? So we have carbon and silicon, which are above the staircase. So it looks like this. We have carbon and silicon above that staircase. And then below it, we have germanium, we have, tin, and then we have lead, and we have fluorovium, which is a fun one. So above these, carbon is a nonmetal, no question about that. Silicon is a metalloid, as is germanium, but tin, lead, and fluorovium are metals. So it actually depends where you're at in group 14 if you're going to gain or lose electrons when you ionize. But 9 times out of 10, we're going to be dealing with either carbon or silicon, and those ones do gain electrons. So they're going to have a charge of -4 up here, and the ones down here are going to get +4 when they ionize. Okay, so on your periodic table, that's actually written for you. Above group 14, you have a positive -4. So that's where that is coming from. It's because that's split there. Charges, a term you have to know. Charges are also referred to as oxidation numbers for reasons that I'm not going to get into right now, but you just have to know oxidation numbers. When I say that term, I'm talking about charges. The next thing to talk about is ionic bonds and compounds. An ionic bond is an electrostatic force that holds oppositely charged particles together. Okay? So oppositely charged particles being an anion and a cation, a negative and a positive. Okay? An ionic compound is a compound containing an ionic bond. So there are a couple different kinds of compounds that we're going to deal with. Any metal plus oxygen is going to be referred to as an oxide. Any metal plus a different nonmetal than oxygen is going to be referred to as a salt. So you've grown up referring to sodium chloride as salt. That's what's on your table. It's what you put on your food. But there's more than just sodium chloride that's referred to as a salt. You can have a bunch of different salts. You could have potassium chloride, you could have potassium iodide, you could have rubidium bromide, you could have sodium bromide, you could have lithium sulfide, you could have a bunch of other things. So all of those collectively are referred to as salts. The goal of chemical bonding is to, again, attain 8 valence electrons in outer shells of atoms. So the overall charge of your compound, sorry, this should say compound, not ion, the overall charge of that compound should be 0. So let's look at calcium and fluorine, okay? If you look on your periodic table, which you absolutely should have in front of you when I'm doing this lecture, you'll know that calcium is in group 2. Therefore, when calcium ionizes, it's going to have a positive 2 charge, okay? So we would abbreviate that Ca plus 2. Or you could say Ca2 plus. Either way, it doesn't really matter to me which order you use. Fluorine is in group 17. It has a charge of -1 when it ionizes. So you would abbreviate that F minus, or if you wanted to, you could even do F minus 1 or F1 minus. Again, it does not matter to me which form of that you use. Either way is fine. Okay? So if you want to think about this for a second, I'm just going to use these two because they have the numbers there. How many fluorine atoms are going to be needed to cancel out calcium's charge? Because calcium has 2 positives and fluorine has 1 negative. So you should need 2 of fluorine to cancel out the positive charge of calcium. Hopefully that makes sense to you. I will show you a couple of tricks to figure this out really quickly. So let's continue here for a second. We just said that you need 2 fluorines to cancel out 1 calcium, okay? Because fluorine has that -1 charge, calcium has that +2 charge. So the easier way to actually just figure this out super quickly and not even have to think about it, you guys, all you have to do is you write out calcium. The metal is always, always, always going to go first. And you put its charge right there. Then next to it, you put fluorine, and its charge is going to go right there. Then you take this number, you move it down and over. And you take this number, you move it down and over. And the compound you get resulting from that would be Ca1F2. And that matches what we originally said. You're going to need 2 fluorines to cancel out that 1 calcium. Now you can simplify this further because that 1 is implied. You don't need to have the 1 there for yourself to know that there's 1 calcium there. So that compound is actually written CaF2. Okay? Once again, let me reiterate a couple of things. When you are writing compounds, the metal has to come first. The nonmetal has to go second. I do not want to ever see you writing this. I will mark that wrong because the metal comes first. Okay? So now I want you to pause the video right now and I want you to take a second and just try these on your own. If you're still not sure, I'm going to explain it, but I want you to just pause it now, give it a shot. So my hope is that you actually did pause it and follow my instructions. If not, I'm going to continue and still explain it because this is notes. So let's take magnesium and chlorine. Magnesium, abbreviated Mg, is going to be in group 2. Chlorine, abbreviated Cl, is going to be in group 17. Okay? So from that information, you should know that magnesium has a +2 charge. It's written on your periodic table, and chlorine is going to have a -1 charge. Okay? Let me switch colors. You're going to do exactly what I just did before. You're going to take this number, you're going to move it down and over. You're going to take this number, you're going to move it down and over. The negative and the positive are just going to go away. And you end up with Mg1Cl2, which again, you simplify to MgCl2. Writing compounds ionically is that simple. You do not need to even think about it. Swap and drop is your friend. So let's try another example. Let me switch back. We have aluminum, abbreviated Al, and we have oxygen, which is abbreviated O. Aluminum is in group 13. Oxygen is in group 16. Aluminum is going to have a charge of +3. Oxygen is going to have a charge of -2. Once again, same process is going to take place. You're going to take this number, you're going to move it down and over, that number, move it down and over. You are going to end up with Al2O3. You don't even need to simplify because both of these have a subscript. And you are done. This is your compound. So let's talk about some things you need to be aware of when you're writing compounds. So let's look at silicon and oxygen, okay? Silicon is in group 14, oxygen is in group 16. So these ones would have a charge of, we have our 4 here, and we have our -2. So silicon, being a metalloid, could act and actually have a +4 instead of a -4. Remember, I told you that group 14 was a little bit split. So when this is happening, when you write silicon +4 and you write O -2 and you do your swap and drop properly, you end up with Si2O4. But what actually happens is you need to reduce sometimes. See how 2 and 4 are both divisible by 2? You're going to do exactly that. You're going to swap, drop, and reduce. So you end up, when you divide both those subscripts by 2, you end up with Si1O2, which then simplifies to SiO2. So if you ever see subscripts like that, you're always going to go ahead and reduce it down. So on a test, if you had put Si2O4, you would have gotten partial credit for doing the swap and drop correctly, but then you didn't simplify it, so you would have lost a little bit of credit there. Same thing if you had put Si1O2. This is not simplified all the way, so you would lose a little bit of credit for that. So make sure you're swapping, you're dropping, and you're reducing and simplifying when that is going on. So let's talk about naming those ionic compounds. I just taught you how to write ionic compounds, but I did not yet teach you how to name them. We have our positive ions and our negative ions coming together to form compounds. Like I said before, ions that are positive keep their name. We just call this the sodium ion, because this is the sodium element as an ion with a charge. So we would call this sodium ion, okay? The negative ions, again, are named with your IDE ending. So instead of oxygen ion, we would name this the oxide ion, okay? If I wanted you to put those together, and I wanted you to name, let's say, this compound, because that's what's going to happen when sodium and oxygen bond with one another, you'd have to name this compound. So what happens is you no longer need ion, and you take this and you put it together. Okay, you take this and you put it together. So the name of this guy would be sodium oxide. Okay? Easy peasy. There are some rules though. Once again, let me reiterate this. You're always, always, always going to name your cation first, or your metal. Your metal comes first. It does not matter. Your metal comes first. For your monoatomic cations, monoatomic meaning one atom, okay? 4 cations that are made up of one ion, not 2, not 3, not 4, but 1, you're just going to use that element's name. So magnesium would say magnesium, potassium would say potassium, strontium would say strontium, sodium stays sodium, lithium stays lithium. Okay, so those are easy. For the monoatomic anions, once again, one atom anions, you are going to use the root of that element's name, but put IDE on the end. So fluorine would become fluoride. Nitrogen would become nitride. Phosphorus would become phosphide. Sulfur becomes sulfide. Chlorine becomes chloride. Bromine becomes bromide, etc., etc. So if I wanted you to name cesium and bromine's compound, cesium's going to keep its name, and bromine becomes bromide. So take a second, look at this one. We have 2 elements here. We have calcium and we have oxygen. Calcium's going to keep its name, so calcium. Oxygen's your anion, so it's going to get that IDE ending, oxide. Your compound becomes calcium oxide. Our transition elements, the fun ones. If an element has multiple oxidation numbers of the same element, or multiple charges, i.e. the transition elements, the name needs to indicate the charge. So this is done using Roman numerals. So my hope is that you have at least heard of Roman numerals before. 1 is written like a capital I, 2 is like this, 3 is like this, 4 looks like that, and 5 is going to look like that. You're probably not going to need any other Roman numerals other than 1, 2, 3, 4, and 5. So my advice to you is write that down somewhere. Maybe, I don't know, on the back of your periodic table. That might help you, because if you don't include the Roman numerals, you're going to get marked wrong. So if we were going to name this compound right here, we would have to give iron a charge using a Roman numeral. Now the naming is going to work pretty similarly to the naming rules I already just taught you. Iron is going to keep its name. Fe is iron, so we're going to have iron. Oxygen is going to become oxide. The only difference is we need to tell what charge iron has, and you can actually do that super easily by doing the opposite of swap and drop. So I'm going to show you how that works. Because I just told you iron can have more than one charge, but you know what charge it has to be based on this molecule, because to make this compound in the first place, swap and drop had to occur. So we do the opposite. We take the bottom number over and up, and boom, Fe plus 3, because that 3 is going to belong to iron. So our Roman numeral that we put in the middle of the name is iron 3 oxide. Okay, and you know you did this right because the 2 belongs to oxygen. We know that oxygen has a -2 charge because it's in group 16. So you'll know that you did that opposite swap and drop correctly. There's your compound name. So why don't we talk about this one for a second next? We have a couple of different elements here. We have copper and we have nitrogen, okay? Another way to write this compound, unsimplified, there's an implied 1 right there next to nitrogen. So to figure out what the name is, we can start just like I started with iron 3 oxide. We have copper, which is our metal, and therefore it's going to keep its name. We have nitrogen, which is going to get that IDE ending, so nitride. And then we just need our Roman numeral there. So how do we do that? Well, we take our number, we bring it over and up. We take this number, we bring it over and up. I'm going to check real quick to make sure I did it correctly. Nitrogen is in group 15 and it has a -3 charge. Look at that, the 3 is going up there. Copper gets that 1. We know that copper is a metal, so its charge is going to be positive. giving it a +1 charge, which means that the Roman numeral in the middle of copper nitride needs to be a 1, copper 1 nitride. Polyatomic ions, polyatomic ions, polyatomic ions. They are fun. I am going to, the next time I see you, give you a nice sheet of polyatomic ions because I'm not going to make you memorize them. But polyatomic ions are ions that are made of multiple atoms, okay? So poly means many. If you've studied history for any length of time, you've heard the term polytheistic before, which means many gods. So polyatomic means many atoms. These compounds are going to act the same way as a singular atom does when you're making ionic compounds. Each one of those polyatomic ions is going to have a unique charge and name associated with it. Once again, I'm giving you a list so that you don't have to memorize them. So here's a few of them that you're going to see a lot. This one is called hydroxide, and it has a -1 charge. This one is called ammonium and has a +1 charge. And this one is called sulfate and has a -2 charge. Okay? Swap and drop is going to work the exact same way when you're using these to make compounds. You just have to treat everything inside these parentheses as if it's never going to change, because it won't. Okay, so let's look at these two for a second. Let's say we wanted to look at sodium sulfate. Sodium has a +1 charge because it's in group 1. Sulfate, I just told you, has a -2 charge. You see that sulfate's in parentheses, so nothing inside these parentheses is going to change, but you can still do swap and drop. This -2 is going to get brought down and over. This 1 is going to get brought down and over to the outside of the parentheses. So when you're writing this compound, we have Na2SO41. And make sure you include your parentheses when you put another subscript here. Because if you didn't, it would look like this, and you'd be telling me that there are 41 oxygens attached to a sulfur, and that is never the case. Okay, so your parentheses are super important. You could then simplify this to Na2SO4. When there is not a subscript, additionally, you do not need those parentheses, but if there is one, then you absolutely do need it. All right, so that is about all I have to tell you about forming and naming compounds today. The only thing I want to add is actually that our polyatomic ions are always going to keep their name. You're never going to put an IDE end on them. It's always going to be sulfate or ammonium or hydroxide or any other name that's going to stay. So never try to change it, because you'll be implying that there's a completely different group of atoms around you. All right, that's all that I have today. So go ahead and make sure you're filling out your note sheet along with this, and then have a good day.